Welcome back. This is lecture 26 in our series, and today we're continuing something we started doing on last video, right? So I'll start with a quick review of where we were going, just so people can refresh their memories. So essentially what I did was to define the 1PI diagrams, right? For now, they're just a definition, but they will be very important pretty soon, right? I can basically, eventually, will be able to separate complicated diagrams into their 1PI components, right? So it is important to know these sums of 1PIs individually, right? And then I was trying to get essentially what is in this first box here, right? I argued essentially that starting from the generator of the connected diagrams, right, I could obtain this object, which I didn't name yet, that would be the generator of the 1PI diagrams. I still didn't show that, right? But that's where we're trying to get. I said, if I do a Legendre, this is a Legendre transform, right? And my point here is that by doing this transform, I will obtain this object, which will be the generator of my 1PI diagrams. And in the process of building this Legendre transform, already I got a very important object, right? This classical field, right? So I was the first thing I did was trying to find which is the conjugate variable to J in this transformation, right? And I found this classical field, which actually classical field is a name that can cause some confusion. This is actually the VEV of the quantum field. So I'm talking about the expectation value of the field in the ground state of the system, in the vacuum, right? And maybe you can understand why we call this classical field if you consider that the external source is also classical. So they are both classical in the sense that these are objects which I'm not doing path integrals over in the path integral formalism, nor are they operators in the operator formalism, right? So this guy includes a lot of quantum effects, but the expectation value itself is not an operator, right? So I'm carrying a lot of information about the quantum behavior of the theory, but in a classical object, right? This is a field, right? Not an operator. And then I went ahead and I have shown that I can rewrite this guy as a recursion relation, right? I wrote this expression for the classical field, which involves the classical field itself. And in the process of writing this recursion relation, I define these objects, which are resummations of the whole series, not resummations, they're the sum themselves, of the whole series for 1PI diagrams, right? So this gamma 1 here, or the pi 2 here, or gamma 3, or gamma n, I just the sum of all the 1PI, the one particle irreducible diagrams, with a given number of legs, of external, each of these functions depend on a number of points, right? So these are the 1PI green functions for a number of points, right? 3, 4, n points, right? So I've managed to rewrite the classical field in terms of these functions. And then I have shown that once I have a proper definition of these functions, it's easy to write this object, right? This gamma hat here, which is the generating function, right? The generating functional for these 1PI sums here, right? I just have to write these essentially as a polynomial on these classical fields. And then of course, if I do the appropriate number of derivatives and then set the classical fields to 0, I get back these objects, right? Since I named the sum of with two external legs differently, I have to make two cases to write the proper expression, but that's all. And I'll make it clear why I'm doing that in a few minutes, so bear with me. Right? So now in the end of last video, I left two missions, right, for today's video. One is to clarify this pi2 story here, right? I will define a gamma 2 pretty soon, right? And to actually prove that either this object or something very similar to it that's related with the pi2 story, right, will actually satisfy this Legendre transform that I put up here. Because the way I got to this gamma hat, for now, bears no relation with the Legendre transform itself, right? So I want to show these two things, and for that I will use the expression I have just shown. Let me start by noticing that in this recursion relation here, right, I have all these functions, like gamma 1, pi 2, gamma 3, gamma 4, gamma n, right? But they are multiplying by a certain number of classical fields, which is always one less than what shows up here, right? So here gamma 1 is accompanied by one classical field, this by 2, 3, and in here gamma 1 is not accompanied by the classical field, pi 2 is just 1, pi 3 is by 2, right? There's one less classical field here, always multiplying these guys. That means I can rewrite this classical field, the recursion relation up there, in this way, right? I can write phi classical of x as the integral of the d for y, right? The propagator, x minus y, the source, j of y. So far, I'm only repeating what I have here, right? d for y, propagator, source. But from here on, I basically have one derivative of this guy in relation to the classical field. That's why I have one less power of the classical field everywhere, right? So I can rewrite this in this way. I can just differentiate gamma hat of the classical field, right, in relation to the classical field on the variable y, right? I hope you can see up here, and go back to that expression, that this is a function of y, right? Z is integrated, same here, right? Z and W are integrated, there's y left, right? For every one of them. So this is just that generating functional differentiated once in phi classical calculated at point y, right? And this is very useful because now what can I do, right? I can apply the inverse of this propagator acting on x, because this is a function of x, right, on both sides of the equation, right? That means that I get this guy applied here, right? And in here, what this will do, right, once the inverse hits this function, I'll get a delta 4 of x minus y, which then I can use to integrate this, make this integral, right, and just replace y by x here and here, right, effectively, right? Once I differentiate these things in relation to phi classical, I'll get functions of x, of y, which then integrated will become functions of x. So that's the same as just exchanging this for an x, right? So let me just organize my equation here, because I'm getting to a very nice relation, right? Now I can isolate the source here. Let me keep the source on the right side here and bring this guy to the other side. Right? So let me just repeat this one. And this comes here as a sum. That's the sum, right? And now this guy I want to rewrite as a derivative, right? It should be clear, but you can easily verify if it's not clear. that this guy is the same as the functional derivative, right, of this one, phi classical. There is an integral here, right, because this now depends on two variables, phi classical of x. So when you go in with the functional derivative, now I have to be careful with the variables here. This is not a function of x anymore. Whatever variable is here is integrated, right? This depended on one variable. Now it is integrated, and when I differentiate in relation to phi classical, right, I can act here or here. And when I want to act here, I can use an integration by parts to throw the derivative there. That disappears with the factor 2, and you go back there. So this is the same as that, right? And now I can, this is the same derivative, so I can write this in this way, right? So all I'm saying here is that when I apply these derivatives here, I go back there, right? And I lose the factor half. And this is equal to j of x. Now this is wonderful, right? Because this quantity right here is what I call the effective action, right? And you could ask why, but look at the equation it satisfies, right? If I write this here, I'm saying that the variation of this quantity in relation to phi classical is equal to the source, right? Just remember what happens in classical field theory, right? If I have an action in the presence of a source, so this is the action and this is the source term. If I do a variation here and I use the principle of stream action, this becomes quickly, right, this, right? This is the same equation as that one. So what I'm saying is, in the same way you can use this equation for a classical theory and solve this to find phi of x, which is the classical field, you find the configuration for the field, you can solve that one, right, using this effective action to get the configuration for this classical field, I mean the VEV of the quantum field. Or another way to say, you get the configuration for the ground state of this quantum system, right? So this is a very powerful quantity to know. Of course, you can only calculate it perturbatively in interacting theory. It's not an easy job to calculate this. But I found an action that includes the quantum effects and allows me to get this object, right? And that's why we call it an effective action. What's more, now I can show that this is given by that Legendre transform I have written before. Let me rewrite it. So something like this, right? Like classical. And now I can substitute this in here and show that this side also satisfies the same equation. What shows me that at most these objects will differ by a constant, which is fine. It's true for any action, right? It doesn't matter. Right? So let me show that. If I take these derivatives and apply here, right, on the right hand side of these equations, what do I get, right? First I need to differentiate W in relation to the classical field. I'll get del W of J del phi classical of X, right? And then this one is easier, right? This is J, just I just differentiate J in relation to phi classical. Remember, they are not independent because they are conjugate variables in Legendre Transform, right? Times phi classical, right? Plus j of x, right? So I have to act with this derivative in j, and then this derivative on phi classical, right? The second one just gives me j of x, and the first one is this. Now this differentiation of w, right? I have to use a chain rule here, right? Which looks like that for a functional derivative, right? This is d for y, right? Del w of j, del j of y, times, this is a chain rule, right? Del j of y, del phi classical of x, right? So this ends up being a function of x, and this is the chain rule, right? I know that j depends on phi classical in some complicated way. We have seen that when I was defining phi classical, this is in the presence of sources, right? You're looking at the vacuum in the presence of sources, right? But I don't need to know, because this part I know, right? This is just the definition of phi classical. So what I'm getting here is, and of course then I can write this as a scalar product again and hide this integral again. This will be phi classical scalar del j del phi classical of x, right? Which is the same term I have here, but with a minus sign. So this, there is a cancellation between these two terms. And this, the only thing left is really this j of x, right? So I have shown that this also satisfies this condition, right? This equation. So I can identify the two definitions, right? Here I used this definition, here I use the Legendre transform, and most they differentiate by something that is zero when differentiated by phi classical, so I can take that constant to be zero and be done with that, right? So I have shown that another way to obtain this guy is through this Legendre transform. I can also use this Legendre transform to write a very interesting expression, because we know that the partition function z of j can be written as the path integral, right, over phi of the exponential of minus the action plus j phi, right? And that's at the same time z of j I used to define the exponential of minus w of j, right? It is understood here, of course, z of j is written in this way, understanding that we're taking vacuum to vacuum conditions here. So whatever conditions I'm using for the path integral, I mean periodic with very large period, right, tending to infinity, makes this the vacuum-vacuum transition, right? But now I can plug that Legendre transform here to write this exponential as minus the effective action in terms of phi classical, right, plus j of phi classical, right, j times phi classical, which I can put here, right? If you look at this equation, right, you see that in a way, right, at least as it regards the vacuum of the theory, I have managed to do the path integral in a way, right? This is just like a partition function of a classical theory with this action, which reinforces this idea that this is an effective action that takes into consideration all the possible quantum effects which are given here by the path integral, right? This is pretty interesting. Now, let's go back to our original, now that we understood this effective action, let's go back to our original program, which was to show that this is a generating function for the 1pi diagrams, right? So in order to do that, let me define now this effective action, or not define, but rewrite it as a sum over the 1pi diagrams. Let me write this one. Let's take n bigger or equal to 1 over n factorial, gamma n, and then phi classical many times, right? There are many scalar products here. In fact, there will be n fields here, n phi classicals, right? It should be obvious that if I differentiate this thing for any number of fields, any times different than 2, then if you go back to the definition here, right, and look at this definition, right, this term will disappear for any number of derivatives which is different than 2, right? And then if I take, say, a number of derivatives, n, where n is different than 2, right? The derivative on this gamma will be the same as with the gamma hat. Right? Once I make all fields equal to 0. Right? So for n, for any of the 1pi functions different than 2, I have already shown that this is a generating function, right? Because I'll get to the same equation I had before. This term disappears if the number of derivatives is different than 2. I get only this, right? And then I have this equation right here, right? And I generate all the 1pi functions. Now, for the number of different derivatives equal to 2, right? That equation, this one, actually implies now a new definition for gamma 2, right? This includes a definition for gamma 2, which is now, let me write it explicitly, right? There's a gamma 2 now that depends on x and y, which is defined as the second derivative of this guy, right? Phi classical of x del phi classical of y of the effective action after I take phi classical going to 0, right? Let's write this explicitly. So this is equal to, well, let's write first, I have a term which is just phi hat, phi classical differentiated in relation to this, when phi classical is 0, right? Plus the second derivative, again, in the same two variables, of that extra term I had, right, which is half of phi classical scalar delta minus 1 phi classical. And the first one we know, right? The first one, we just have to go back for two derivatives. We go back to one of the first equations we saw today. This one, right? If I do the second derivative of gamma hat, I get just pi 2, right, of these two variables. So that part is easy. And implies that this is just pi 2 of xy, right? And the second part, we know, right? We know that the first derivative acting here, we actually did this derivative backwards before, right? We know that this is the same as del phi classical x, and the first derivative acting there gives me delta minus 1 y, right? Phi classical y, right? So that's what the first derivative does. I can apply it here, apply it there, and I get rid of the half, and I get this, right? The second derivative will of course act here, right? And give me, right, the effect of this derivative on a Dirac delta of x minus y, right? Of course, I can make sense of this by writing this Dirac delta as a Fourier transform and then acting the operator in there, right, in the exponential of the Fourier transform, right? So that means gamma 2 is now given by pi 2 of x, y, plus this thing, right? Let's call it a thing, right? It's an operator, but it needs to be acting on something eventually, right? Otherwise, it makes little sense. But this is important. This is an important object. It's important to see that the 1pi functions are really these, right? This is the sum of all 1pi functions. But now, when you take the effective action, you generate this little extra piece, right? Which is very important because this object actually has a meaning, right? And it is the inverse of the full propagator of the theory, right? This is the inverse of the full propagator. This is the inverse of the free theory propagator, right? And this is the inverse of the full theory propagator in the sense that if I define this full propagator, I'll be able to show that the integral over d4z of this guy, gamma 2 xz, contracted with, let's call this delta f c. C means complete, the full propagator, right? Of z minus y, right? If I act this here, I'll get or something proportional to x minus y. But in order to prove that this is so, right, I have first to define this guy. That's the next thing I want to do. But for now, I want you to notice, right, that I actually managed to show that the effective action generates all the 1pi diagrams. But in the case of the 2-point 1pi diagrams, it generates this little extra piece, which is actually important. This object is more interesting for us than just the sum of all the 1pi diagrams. And we will understand why you need this extra piece to have a physically important object, right? So let's go on and define this full propagator and show that this is true. In order to define this full propagator of my theory, I'll make use of the 2-point connected function, right? And the logic is this, right? We already know, for instance, for lambda phi 4, right, that the free theory propagator is this, but in lambda phi 4 you expect corrections that look like this, right? Including 1pi diagrams. And of course, also 1pr diagram, right? One particle reducible diagrams. These are all here correcting this free theory propagator, right? This is in position space, but you can go to momentum space too, right? So I would expect, right, naively, that the full propagator is described by all the connected functions, so not just the 1pi, but also these, right, in the absence of sources, right? So let's try to properly define that, right? So we already did define before the 1-point connected functions, right? Let's do the same for the 2-point connected functions, right? These guys are functions of 2 variables. And let's start that with in the presence of sources, because we need that to do the derivatives, and we take the sources to 0 at the end, right? We know who's the generator of the connected functions, right? It's W, right? Minus W, in fact. So let's write this 2-point connected function in this way. So a derivative in Jx, a derivative in Jy, right? And W of J, right? So this guy, we have already shown, should generate all the 2-point connected diagrams, right? But of course, now we know that this, right, with the minus, is the definition of the classical field. So I can also write this as the derivative of the classical field in relation to the source, right? Because we know that this is the classical field, right? Which allows me now to go back to the recursion relation for phi classical. Let me take a look. Remember, we are differentiating in relation to the source, right? So let's go back to the definition on the recursion relation, right? And take a look at what that derivative would do for us. That's far up here, right? So it would act here, right, giving me a propagator, and then I have a bunch of del phi classicals in relation to J, right? Because phi classical is also not independent of J, right? So I have a bunch of derivatives in all of these fields, right? Let's write that explicitly down there. Okay, so now let's write that, right? So G2 goes here, right? The very first term is just, as I notice up there, it's just this propagator, right? And the second term is, of course, then there was a term like gamma 1 that does not depend on J, so that one goes away, right? And then there is the term that involves pi 2, which was delta times pi 2, right? Times the classical source, right? Which now I have to write as a derivative in J, right? And that's all a function of Y, right? Just by logic here. I still have the derivative in J, so this whole function has many scalar products here, but it should be a function of Y in total. And there are other terms, right? All these other terms will be proportional to at least one phi classical that is not differentiated like that, right? Because they have bigger powers of phi classical, right? At least phi classical square, right? So when I differentiate in relation to J, one of these phi classicals is left undifferentiated, right? And that means when I make J equal to 0, which is the next step, I have to wonder, right? For most theories, it is true that phi classical of J equals 0 is also 0, right? This is true for all theories that have a trivial vacuum, right? Where if I remove external sources, the vacuum is just 0, right? And this is also true for theories with spontaneous symmetry breaking, because in those theories, I can always rewrite my field. If I find a field that has a non-zero VEV, right, I can also always rewrite this field as another field plus the VEV, right? And effectively do my whole theory in terms of a quantum field that has a VEV of 0, right? So I assume that is true for the theories, and of course there are some very non-linear complicated theories that have instantons, and those are solitons, and those are more complicated. But let's assume that if phi classical is 0 when j is 0, that means I can ignore all those terms, and this is true for most theories, and rewrite these as I take j to 0, right, as these. Let me write this one here. Now j equals 0. These I just copy down here. Right? This term stays the same. I want to explicit my scalar products here, right? And make them explicit. So let's call, there are two scalar products, so two integrals, d4z1, d4z2, right? I have this propagator from, this is the guy that depends on y, right? It's y to z1, right? Pi 2 depends on 2 points, z1, z2, right? And these guys again, right? This derivative of phi classical in relation to j, if you go up here, right? This is the full propagator, right? So I found also a recursion relation for the propagator, right? This is g to c of z2 x, x, in the absence of sources. And now if this is true, all the other terms here are 0, right? So I found this recursion relation for this connected function. Now let me use a trick here to rewrite this guy here as an integral, right? Let me write this as d4z2, right? Dirac delta y minus z2 g to c of x z2, right? Again, in the absence of sources, but I'll suppress that notation for the sources. Now we're working in the absence of sources. Writing this as an integral allows me to bring this term to the left-hand side of this equation and group these two integrals together. I'll put this d4z2 in evidence, right? So I can write this equation as a d4z2, right, which acts, which integrates Dirac delta 4 y minus z2, right? And I'll bring this g2c outside these brackets, right? So what I still have on this side is now delta. I have another integral, so there's a d4z1, right? This sign has changed because I brought it to the other side. There's a delta y minus z1, right? Pi 2 of z1 z2, right? And this is all multiplying this function here, which I'll write g2c z2x, right? These are all symmetric in the exchange, this because I'm talking about a scalar field, right? So this is delta y minus x, which is here, right? I just put this to the other side and group them together, right? Now I can take a look at this equation, right, which is an important one. I'll use that again later. But now just to prove what I want to prove, I can apply on both sides of the equation the inverse of this propagator, the free propagator, Let's apply that on both sides, right? On the left-hand side, I keep this integral d4z2, right? I'll have this inverse of the free propagator acting on the Dirac delta, plus now here this inverse hits this guy, becomes a Dirac delta of z1y, which allows me to integrate in z1. So I just replace z1 by y here. This becomes by 2y z2, right? And this is all acting on this guy. And of course, on the right-hand side, this just acts on the free propagator and becomes a delta y minus x. Right? Now look at this. The thing that appeared in here, this, is again gamma 2 of y z2, right? Which proves what I wanted, right? Look, if I go back here, this is what I wanted to show, right? This is contracted here, z is integrated. Down there it's called z2, but I'm showing that when I apply this gamma 2, right, to the full propagator, which I'm identifying with all the 2-point connected diagrams, right, I get a Dirac delta, which shows that this is, in the sense, the inverse of that green function, right? And makes a little bit of sense of this operator, right? This will basically take z2 here, replaced by y, because I can do this integral, and then I differentiate g in y, right? The derivatives here will act on this guy after I apply this Dirac delta. And since we're talking about the full propagator of the theory, there's a very important result we can glimpse by looking at this equation right here. Right? Let me write it first in a very simple way, right? Just contracting all these scalar products, right? You can see that this equation is really just 1, because this is I can use this integral just to exchange z2 by y here, right? So this is 1 plus delta scalar pi 2 scalar g2, right? This 1 is just g2, right? When I do this contraction, right? And then both z1 and z2 are contracted here. So this is these are those two scalar products there. And the other side, I just have delta. So a simple way of writing this equation without keeping detailed track of the positions, right, is this. But now this is very useful, right? If I write this equation down here, right, this is valid for the full propagator, I can, right, if this is inversible, right, I can write this as d2 is equal to identity plus, right, delta pi 2 minus 1 contracted with the free propagator, right? And this expression is already important on its own, but it's easier to understand what's going on here if we make a series for that. Remember, when I did that resummation up there, when I did that recursion relation, in a way I'm resumming the series. So I want to undo that, right, in a very particular way. So I can use this series, right? We know that this is equal to 1 minus x plus x squared plus minus x cubed, so on, right? I'm not truncating that sum. I'm thinking about the whole sum, right? That means I can write g2 as 1 minus delta pi 2. Remember, there's a scalar product here, but I'm suppressing everything to make life easier, right? Plus delta pi 2 delta pi 2 minus delta pi 2 delta pi 2 delta pi 2, right? I'm just using this expansion here. All of that multiplying the free theory propagator. This is the complex, the complete propagator. This is the free propagator, right? So in first approximation, remember these guys have powers of lambda. If I take lambda to 0, right, in a lambda phi 4, but if in general, if I take the interaction to 0, all this goes away, and then the two propagators are the same, right? But this series now is looking like delta minus delta pi 2 delta plus delta pi 2 delta pi 2 delta, right? And so it goes, which in diagrams is saying that, let's call these right, all the connected diagrams, right? So this is the full propagator in the absence of sources, right? It's all the connected diagrams. In fact, using my notation, I could even suppress the C, right? Circle already means connected diagrams. If you look at this expression, the first term is just the free theory propagator, right? The second one is the free theory propagator goes to one insertion of all the 1pi diagrams plus free propagator, one of these, free propagator, another one of these, right? This term here, free propagator. The next one will have 3 of these yellow circles, right? It's a minus. 3 of the yellow circles, 4 of them, which is the series for the all diagrams, right? I can just remember, I could do this, right? Plus this. Again, I'm going back to lambda phi 4 because we have more intuition of what should show up, right? So both of these are included here. This is included on this one, but also now I have these right here, right? So that's what I meant when I said sometimes you can take very complicated diagrams and rewrite them in terms of 1pi diagrams. Each of these diagrams now go to arbitrary high powers in the interaction, right? Because there's lambda to any power in here. But I organize that as a sum of 1pi components. And I can resum that, which is what's written right here. This is the resum of the resummation, right, of this whole series right here. Of course, you have to calculate pi 2 to some order in perturbation theory, but this series is all included in here. And remember, this is the first time we actually get a glimpse, right? I told you already a few times that the free theory propagator is something like that, right? Where this is the mass in the Lagrangian, and the full theory propagator will be something different, like this, right? Now you're seeing that this thing is going somehow into the denominator here, right, of this multiplication, right? And somehow I'll be able to rewrite these in this way. But that's the correction that will make the free propagator into something more complicated. So the z function and this, whatever this new pole is, must come from this object that I'm multiplying here. We will use the sum of all the 1pi diagrams every time we want to make some general statement about the full propagator of the theory. For instance, eventually we will use a sum like that to show that in the case of a photon, these contributions will not generate mass for the photon. And we can show that for the whole series. We're summing the whole series, not doing perturbation theory, right? We're summing it all, which is a pretty nice thing to be able to do. So this series here is a very important one that we use a lot, right? This resummation of all the 1pi diagrams that is already here, right? This is the result. Another object that we can extract from this effective action is the effective potential, right? So when we define the effective action, right, we wrote it as an expansion on powers of the classical field, right? Multiply the coefficients turn out to be the 1pi function, right? These 1pi sums. Right? But I could have done this differently. I could write a different expansion for the effective action, which is sort of a Taylor series for the classical field, right? In terms of derivatives of the classical field. So that would look like something like this. And I named the first coefficient minus u of phi classical, which is a function of x. Now these are functions, right? And the rest of the series will be just derivatives, right? So the next term would be derivatives of phi classical square, and with some other coefficient here, which is a different function of phi classical, and so on, right? I could make a series. Now I have power 4 on the derivatives. I'm making a series on the derivatives of phi classical, right? And of course, if, remember, phi classical is the vacuum expectation value of the field. Suppose this is constant, right? Suppose this is a constant field, right? Then all derivatives go away, and this guy comes out of this integral, right? Because it's not a function of x anymore. And then I get this relation between the effective action, right, and this function u here, right? You just have the volume of space-time times u of phi classical, right? Which is a constant now. It does not depend on x. Okay? This is what we call the effective potential, this guy. And you can show that actually if you go to the classical limit, take the quantum effects away, right? This reduces to the potential, the classical potential V for a field theory, right? And this is a very useful object, because many times, especially when we're talking about spontaneous symmetry breaking, but in general, when you're discussing the properties of the ground state of these theories, right, you're trying to minimize some potential. And of course, the classical potential does not mean anything anymore, right? So the object to use is this one. Just like the effective action, this effective potential encodes all the quantum effects that might change the vacuum expectation value of the field. So if you want to know on the expectation value of the field in the ground state, that's a very useful quantity. In fact, if you go back to the equation for the effective potential, if you remember, right, was something like the variation of the effective action in relation to this guy was the source, right? If there is no source, right, this condition applied here quickly simplifies to this one, right? When calculating the field in the vacuum, right, is equal to 0, showing me that minimizing or extremizing this this, minimizing in this case, this potential, will give me the value of the field, and you can use that to discuss spontaneous symmetry breaking in quantum field theories, just like you would for classical field theories. You just replace the potential by these effective potential now, right? Which is again another very important object to have. As a final comment on this limit of going to the classical theory, let's think a little bit what happens when I actually do away with the quantum effects. Like I said, for in this case, this guy becomes the classical potential, right? But let's see what happens with the classical action. So we know that our theory, we already wrote this equation here, which is the partition function for quantum field theory, and I have argued that this is the same as this, right? But let's see what happens with this equation in this limit, right? We know that if I go away from the natural units, right, there would be a 1 over h bar here, right? And that means that if I take this to 0, this becomes a very big number, which increases a lot the exponential suppression for any configuration of the field that is not an extreme of the action, right? Essentially, when I take h bar to 0, this is dominated by the extreme of the action totally, right? So the only configurations that matter in the path integral will be the solutions to the classical theory, right? The extremizing of this action, right? And then this becomes this, right? Essentially, effectively, I have something where this is the answer of my path integral, right? It's the same as this, and effective action becomes the action, and vice versa, right? In that case, you could ask, if this is a generator of diagrams, right? In this case, the 1pi diagram, right? What does the classical action generate? Can I look at the classical action, right, as a generator of functions, of diagrams? And if so, what diagrams would it generate, right? To see that, to see the answer to that, let's think of a simple case. And as always, I appeal to the lambda phi 4, right? So this would be the action in that case, right? There's an integral here and a d for x of phi x to the 4th, right? This would be the action for lambda phi 4. I even forgot the lambda, so there should be a lambda over 4 factorial out here, right? So then if I use the extreme action principle, this becomes this equation, right? And the solution to this is the classical configuration of the field, right? So using this up here, I get another equation. I'm just varying this in relation to phi. And I can formally solve this equation just multiplying by the inverse of this operator, right? And write phi of x is equal to delta scalar j, which is a function of x, minus lambda over 3 factorial delta phi cubed, which is also a function of x, right? This is a formal solution to that equation, right? Now I can use, and again I'm writing this formal solution as a recursion relation, because phi of x shows up on both sides of this equation. Now I can do the opposite I did before, right? In the case of the classical field, I wrote the diagrams and I resummed them to get to this recursion relation. Now I'll use the recursion relation to get the expansion of the diagrams, right? Which are all already contained here. So what I'm saying here is that if the solution, this classical field in this case, which is really classical, now it's not the VEV of something, it's just classical field. I mean, they both coincide. It's also the VEV in the limit where h bar goes to 0, right? But in the presence of sources, right, this is what I'm calculating here, right, will be, in this case, right, this term in terms of diagrams is just a propagator from x to the source, and this term is just minus lambda. I can omit this 3 factorial because that's a symmetry factor, right? There's a propagator that goes from x to a point that is integrated over. That's where the vertex is, right? And I have at that point 3 times the classical field, right? This phi, which is the same as this guy. So I'll indicate like that. That's the whole series again, right? I can put 3 small circles here. Right? And these are the full series again, right? This is the same guy as here, but calculated at a point z that is integrated over this point, right? This is actually the whole recursion relation, and the 3 factorial is all the permutations you can do with these 3 guys here, right? But I can use that again, right? I can use the same diagrammatic expression back at these 3 points, right? So this guy stays here. I put a minus lambda here. And now the first term I would get here would be the same thing, but put this first term of the expansion in each of these 3 guys. Source. Source. But of course now I have more terms, right? I don't care about this coefficient, it's just some numeric factor, some power of lambda, I don't care, right? But the next thing that I could put here, right, this is containing here, it's actually contained in that diagram, right, would be something like the line goes to another vertex that then goes to 3 times the classical field again, which I could put here or here, and I could keep, right? There's more terms now. I can put the 3 of them here, 3 of them here, and I could come with this recursion relation back here and substitute in this 3 and keep branching. And the key word here is branching, right? I hope you can see now that by doing this process, all I can do is keep taking one of this line, branching into 3, and then again, and then again, and then again. I'll never get loops out of here, out of this, right? By using this recursion relation, I get all 3 level, and that's why you call it a tree level, because it looks like a tree, right? It's branches, right? I can get all 3 level diagrams for this theory, but I would never get a loop, right? And that's a very important fact, right? We'll see it again and again, which is that the loop expansion of these quantum field theories is equivalent to a h-bar expansion, which means that the quantum effects are really coming from the loops, right? And not the 3 level diagrams. Right? Sadly, we don't have the time to delve into loops too much in quantum theory 1, right? So we'll look those loops and the genuinely quantum effects in quantum field theory 2. But keep that in mind, right? When you're looking only at tree diagrams, what you're really looking is a diagrammatic expansion of a classical field theory. Of course, there's interferences, there's scatterings, but that's because you're looking at a classical field through correlations. And of course, effects in a classical field theory, they propagate as waves. So there are wave effects and interferences and scatterings like you would in quantum mechanics. So this is very good in reproducing the scattering of plane waves, wave packets, all of that you can do here. But the intrinsic quantum effects of a field theory, of a quantum field theory, will only come once we start looking carefully at those loops, right? And we'll do that through renormalization. We'll learn about the running of coupling constants and other effects, right? Which are not, we have not looked yet, right? So keep that in mind. Well, this is all I wanted to say for today. It's kind of a short video, but heavy on the conceptual aspect. So take your time to think about it. Read as much as you can about these effective potentials, because they give you a lot of intuition about the theory we're dealing with here. And see you next video.